Hi there. Let's open this optical mouse and understand how it works. Shall we? Good. So, as soon as we crack it open, the first thing we see is a big brown board in this case, with some buttons, the tracking wheel, and some other components, some more important than others. The most important thing on this board is the main controller integrated circuit, the main IC, which also includes a digital image processor. More on that in a moment. We also see a tracking LED. This can be a visible light, in this case it's a red LED, or it can be infrared, so that it is not disturbing to the eye. We also see a lens, which focuses the light from the LED down onto the surface. The idea is the light will reflect from the surface and come back from the ridges of the surface and come back to the through another part of the lens into a pinhole beneath the main controller IC and land on a sensor array, which will help determine how the image below has changed between two successive positions of the mouse, thus determine which way the mouse went. We'll talk about this in a moment. There is also another decorative LED, but that serves no functional purpose. Let's first take a look and play around with the board. Then we'll get to the theory of explaining how things work. Let's play with the buttons first. So you see the clicky sounds come from these components. I used to think they came from the plastic casing, but no. The plastic casing only has some ridges which push down onto those tiny red buttons, and these are the ones that make the nice clicky sound. Here we have the pinhole for the DSP. Here we have the lens, which you can see has two parts, one focusing the light up and one focusing the light down onto the surface. They are both visible here. One of them takes the light from the LED and sends it below, and the other one captures the reflected light from the surface and sends it up to the little hole in the microcontroller to the sensor array to be processed by the DSP and determine the motion that has occurred. Okay, but how does this actually work? Let's take the following practical example. Let's choose a frame from the video I'm just making. And now let's imagine we're zooming in on the piece of paper in the background of the scene. And this zoomed in rectangle, which the zoom happens to the lens, is then passed on to the sensor. And the sensor sees something like in the red square in the bottom left, bunch of black, white, gray pixels, different intensities. To better illustrate this point, let's search for piece of paper and the microscope on Google. We get a bunch of pictures. Now, if we actually are to zoom in on the paper, you see this pattern that I was talking about of different color intensity, black and white pixels. Now, we took this example of paper, but it can be any material, doesn't have to be paper. But whatever it is, in the end, if we zoom in a lot, you get a bunch of different colors and different light intensity pixels. It's easier to give an example with black and white, so we'll stick with that. Now, let's do something useful with these pixels. This image that we see here, through the eyes of a computer, is seen as this matrix of numbers below. How is that? Well, if we assign a number to each color intensity, black 0, white, so the whitest that we can represent, let's give it the number 255, and then any shade of gray in between, also assign it a number. So for example, mid gray being 128, then we are literally transforming this pixel image into an array of numbers. A quick observation, why did we choose 255? Well, 255 because in computer memory 1 byte has 256 values, as many numbers as there are between 0 to 255, which is 2 to the power 8. And each of these numbers, so let's take 116 for example, if you represent it in binary, you need 8 bits to represent it. Now, we're not going to go into much detail of this sort, just briefly wanted to mention that here we can put actually any number like 100, 1000, doesn't matter for the algorithm we're about to discuss, but it is 255 for good reason. It doesn't affect the algorithm, but yeah. Okay, so now on to the algorithm. First thing I want to discuss is subtraction. So if we subtract two colors from each other, given their number representation. So we have here 5 shades of gray between black and white. Also the same 5 shades of gray on this vertical line as well. Now if we are to subtract 0 from 0, we get 0, 50 minus 0 is 50, and so on. So if we subtract 0, nothing changes. Now what does it mean to subtract from the color black this shade of gray? Well, that would be 0 minus 50. Now we use the absolute of minus 50, which is 50. So whenever we get a negative value, we simply flip it. Now we take another random example. So how much is let's say 50 minus 255? Well, that will be minus 205, and then if we take the absolute value, that will be 205, so we get this shade of gray. Now how does this subtracting of pixels between one another and this particular way of taking the absolute value help us? Well, let's go further. Let's have a look at our magnified piece of paper again and take 2 snapshots of what the mouse sees. So at one moment in time, the mouse sees this picture beneath it. Let's copy it and paste it into this small image I have over here, 100 by 100. So this is what the mouse sees at a particular moment in time. Then we move the mouse like this, like this, so we're moving the image, in other words. And now let's take another snapshot of what the mouse sees. This is only approximate because I'm not sure I chose the exact number of pixels. Oh, I did. No, almost. I almost. But anyway, now how does the subtraction difference help us, the difference between 2 pixels, help us determine which way the image has moved and consequently which way the mouse has moved? Well, here's what we're gonna do. This second snapshot, we're gonna put it in the second layer, and now the blend mode between these 2 layers, we're gonna call it difference. So in other words, what we're gonna see on the screen is the difference between everything we put in this layer. So come on, so this image, the difference between this and this. Let's also add the black background, and let's do this. So you see, when I overlap the images, we get different colors of gray, other colors which represent the difference that we just discussed a moment ago. And now what the algorithm does is simply go through each one of these possible combinations like this. So scroll, 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 down a few lines, scroll, 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 and it goes through all the combinations. And at a given point, we will see, if I can actually find that point. There we go. See? Now, in this position, the difference is 0. That's because this part, this rectangle, is actually part of this other rectangle. because when we selected this rectangle and then the previous one, this little part was the common part, so this is the common part. So now we know that we moved under this direction, so we moved 1, 2, 3, 4 pixels down and 1, 2, 3, 4, 5, 6, 7, 8 pixels right. So we determined the movement on the x-axis and the y-axis by comparing the pixels with this algorithm. So that is, in a nutshell, the way an optical mouse works. It emits a light from a diode through a lens, which drops onto the surface below, gets reflected through another lens, hits the image sensor array. Then the integrated processor, compares these images, these snapshots, and using a difference algorithm similar to what we've discussed here, not the same obviously, this is oversimplified, but something like this, it determines the movement, so how much has the image shifted on the x and the y coordinate, and that is equivalent to how much the mouse has moved, and it sends this information to the computer. This process is of course repeated many times a second. And that's all folks. If you like this video, please subscribe. Thanks for watching.